This video is going to be about a quantity called flux, which is useful in all kinds of areas of physics, but we're going to be talking about it coming up in our study of electric flux. But what is flux in general? Well, it comes from a Latin word, fluxus, which means flow. And flux is a thing we can use anytime we want to measure how much of some quantity passes through some surface. So suppose I have a surface here like the end of a pipe. This idea of flux came from a lot of the physicists who figured out electricity and magnetism in the 19th century were also fluid mechanics. So they studied the flow of ordinary fluids, and they imagined that electricity and magnetism behaved like fluids, which fortunately there are a lot of ways they do. So the mathematical tools for understanding those things are similar. So we've got our pipe here, and I want to know, let's say, the mass flux. How much mass is passing through the end of this pipe? Well, I need to know a couple things. I need to know the density, there it is, which is the mass per volume. And I need to know how fast is that fluid going, the velocity. And I need to know how big is this area. Here we've got that's a meters squared quantity. Here I have a meters per second quantity, and this one's going to be a kilograms per cubic meter quantity. So what do I do with these three things? Well, if I broke the end of this pipe up into little bits, and I called each of them dA, d area, this little guy, dA, then I just want to add up how much velocity goes through each little bit dA. So let's see how that would work. To find the mass flux, we use the Greek letter phi because it sounds like F for flux. That's going to be the integral over all this area. And here, instead of using a lower and upper bound, I'm just using one bound to mean cover all the area, why don't you? So here I have the density times the velocity, and then we're going to use our new product, the dot product, between the velocity and this area element, where an area element is pointed vector-wise in the direction that it faces. So if I had some complicated curved surface here and I broke it up into little curved bits, each of them would have a d area vector pointing perpendicular to itself. And I need to know that when I'm computing flux. Let's take a look at why that's the case. Why does flux depend on this direction? Well, suppose I wanted to know how much vector is passing through this tape. Well, here we can see a couple hundred dots, but what happens if I rotate the shape compared to the vector field? I see I'm getting a lot fewer vectors poking through there, and here I'm getting more. So when these things are most perpendicular, the area and the vector field that's passing through it, that's when we get the most flux through there. So, computing this mass flux, I see I've got my, what are these? Kilograms per cubic meter times my velocity, which is meters per second, times my d area, which, since it's an area, is obviously meters squared, so my meters cubed cancel out here, and I get kilograms per second, which shows me that this is mass per time, and that tells me how many kilos of water, say, are flowing through this pipe per second. So we're going to apply this idea of flux to several situations involving electricity and magnetism. What are the things, just to review, that flux depends on? It depends on the density of the vectors passing through the area. It depends on how big the area is. If my area is just not that big, I won't get much flux through it, even if there's vector outside that area. And it depends on the orientation of these things. We care about the dot product, so when we're defining flux, it is equal to add up all of the, whatever the vector field is that we care about, maybe it's the electric field, dot product with the area. And remember, dot product of two things is the magnitude of one times the magnitude of the other times the cosine of the angle between them. So that's an introduction to flux.